So we talked about last time how we have the octet rule, right? How most of the elements want to have 8. We already learned about one exception, which is hydrogen. Hydrogen wants 2, but we are going to be talking about a couple more exceptions, okay? There are 3 main exceptions. The first exception that we have here is sometimes molecules, when they have an odd number of electrons, you can't give everybody an octet. So here on 9.19, we have 2 examples of that. Or I guess it's one example. We're trying to figure out which is the better structure. We have NO. And so if you guys count up how many valence electrons they have, how many valence electrons does nitrogen have? Yeah, there's 5. Okay, nitrogen has 5 valence electrons. And how many does oxygen have? 6. So if we have NO, the only electrons that we have to work with, we have 11, right? Which is an odd number. And so here we cannot give everybody an octet. And so what we have to do is we need to make a Lewis structure where one of them will not have an octet. Okay, so that's the first exception to an octet rule. It's when there's an odd number of electrons. Now, we can have 2 different structures. So let's just think about which one of these structures will be the most dominant. So here we have one where nitrogen does not have the octet, and here we have one where oxygen does not have the octet. What I want you guys to do now is I want you guys to use formal charge, the equation that we learned last time, and I want you guys to figure out which one of these is the dominant structure. Okay, so I'll give you guys about a minute to try that. You might want to go back to the equation for formal charge. If you guys forgot, formal charge is equal to the number of valence electrons minus lines minus dots. Okay, the number of bonds and lone pair electrons. Take a minute, try that out, and then we'll go over it. All right, I'll give you guys maybe 15 more seconds to finish that up. The thing turns off. Okay. Yeah, it auto turns off. All righty, you guys ready to go? Okay, let's calculate some formal charge. Let's figure out which one is the most dominant. Okay, so we're gonna start with the formal charge of the nitrogen on the left. We know that nitrogen has 5 valence electrons. There are 2 bonds, so 5 minus 2. And then we need to subtract the lone pairs, 1, 2, 3. And that's gonna give you a formal charge of 0. So this nitrogen has a formal charge of 0. Okay, oxygen right here, we know that it has 6 valence electrons. It has 1, 2, 3, 4 dots and 2 lines. So minus 2 minus 4, and this oxygen will have a formal charge of 0. Okay, next we're going to go to the other structure. We have nitrogen, again, 5 minus 1, 2 lines minus 4 dots. So the formal charge on nitrogen here is -1. And for oxygen right here, we have 6 minus 2 minus 3. And so oxygen will have a formal charge of +1. Now, we learned last time that there are two things we want. We want everyone to be 0, or we want the more electronegative ones to have a negative formal charge. So which one do you guys think is a better structure, left or right? Yeah, left is obviously the better structure, right? Because everybody has 0 for the formal charge. Now, some of you guys might have thought about this, but there's actually an easier way to do this without even doing formal charge. Which one is more electronegative, nitrogen or oxygen? Oxygen is more electronegative, right? And we said that if an element is more electronegative, it's better at holding the electrons, right? And so if we think about this logically, which element is going to pull the more electrons to itself? Oxygen. And so if you take a look on the left one, it has 1, 2, 3, 4 valence electrons. Here it only has 3, which doesn't make sense because nitrogen is not strong enough to take away the electrons, right? Oxygen's a better looking guy. He can get more people or more ladies to like him and vice versa, right? Nitrogen's not that good looking. So only a couple people, nice people go to nitrogen. Yeah. Okay. This could be Josh. No, I'm just kidding. Oh. It's because Josh lied to me about the announcement, so I'm still salty. Yeah, so this is the better structure, and you could have done it with the formal charge, or you could have done it just by looking at the electronegativity. I'm sorry, Josh. You're a very good-looking young man. Okay, I mean that in the most platonic way possible, though. Thank you. Gotta qualify because there's all those weirdos out there nowadays. Alrighty, ready to move on, guys? Okay, the other exception to the octet rule is going to be when an atom can hold less than 8 valence of electrons. We already learned about hydrogen, how hydrogen can only hold 2 because it's so small. And another exception that's notable that you guys might want to know is boron. We actually looked at this in a previous example, but boron is kind of weird because it can hold 6 or it could have 8. It could be happy either way. So on the left, we have an example of when boron can have 6 valence electrons. And then on the right, we have an example where it has 8 valence electrons. So either or works. When you have boron, just use up the electrons. Try to put it on the more electronegative ones first, and then it could have 6 or 8. That's a notable exception that you guys might want to know. Okay. Any questions on that one? That one you just need to kind of memorize. Okay, you guys ready to move on? Okay, let's move on to the final example of the exception to the octet rule. Lost my train of thought there. And sometimes it's going to be when atoms can hold more than 8 valence electrons. Now, we learned that if an atom is too small, it can only hold like 2 or 6, right? Now, the opposite is true too. If it's super big, it can hold more than 8 valence electrons. Now, when we have molecules like this, we call the central atom hypervalent because it can hold a bunch of covalent bonds, right? I'm not sure if that's the real reason why it's called hypervalent, but that's kind of how it makes sense to me. There's a lot of covalent bonds there. It could hold more than 8. Now, one very important thing that you guys want to remember about these hypervalent elements is that only elements from period 3, so the 3rd row and below, can hold stable hypervalent compound. So the most common one or the smallest one that usually pops up is phosphorus, P. If you take a look at it, it's on the 3rd row. So P is usually the first or the smallest central atom that can hold more than 8 valence electrons. So P is usually the smallest. That means S can do it, Cl can do it, Br can do it, I can do it, Xc can do it, right? But you can't have things above phosphorus like carbon or silicon or nitrogen. They can't be hypervalent. Okay, so we have some examples here. So if we take a look at XF4, Xe has how many is that? 10 valence electrons in the middle. Phosphorus also has 10. Oh, sorry, this is 12, 10, and we have 12 here again. Okay, so the point is, sometimes when an atom is super big, it can hold more than 8 valence electrons. Okay. Any questions about that? It's just me, or are there less people here today than normal? Yeah, I guess not a lot. Man. Alrighty. Let's move on. So what I want you guys to do is we'll do one practice problem for hypervalent, or not hypervalent, I'll say exceptions to keep it more vague. But I want you to draw the Lewis structure for XEF2. XEF2. Okay, so same rules as before. Count up how many valence electrons you have to work with, and then draw the structure, put it on the more electronegative ones first, and then try finishing it up. Okay. You need cream and sugar or milk and sugar? It's gonna be in the fridge, so you can just grab it. Yeah. Alrighty, you guys need a little more time or ready to go? I'll start talking then, and then if you're finishing, you can finish. But if you're done, we'll just go over it. Okay, so if we look at XEF2, now F is really easy because we've been looking at how many valence electrons does F have? 7, good. Just count the boxes. XC is the one that's a little bit weird because it's on those lower rows. But what we're gonna do is we're just gonna count the boxes same as normal. 1, 2, but we skip this middle. 3, 4, 5, 6, 7, 8. So XE is gonna have 8 valence electrons. Okay. Okay, so we have 8 plus 7 plus 7, 14. Thank you, 22. It's too early. Okay, 22. Okay, so we're gonna put XE in the middle because F is more electronegative than XE. And then we're gonna put the F's around it because F is the most electronegative. And so we're gonna draw 2 lines. That's 2, 4. That's gonna get me down to 18 valence electrons. Now, we want to put a bunch of the lone pairs on the fluorine first because fluorine, again, is more electronegative. So we're going to put 6 on the fluorine and 6 on the fluorine. So that means we've used 12. Okay, so we have 6 left. Now, we don't really have anywhere else to put it except on XE. So all we're going to do is put 6 more onto XE, which is okay because XE is a big atom. It has a big heart. It can take the electrons. And so this will be the correct structure for XEF2. All right, which makes sense because Xe is really big. It's towards the bottom of the periodic table. And so it can hold all of those valence electrons. Okay. Any questions? All righty. Let's move on to the next section. Now we're going to talk about how strong these covalent bonds are. We touched on this earlier about a single, double, and triple bonds, how triples are the strongest because there's the most electrons shared, doubles are a little bit weaker, and then singles are the weakest covalent bonds. Okay, now the stability of a molecule, how stable a molecule is, depends on the strength of the covalent bonds, which makes sense, right? Because the bonds are the things that keep the molecule together. And then the strength of a covalent bond, we determine it based on the energy it takes to break that bond. Okay, that's called the bond enthalpy. And bond enthalpy is the enthalpy change, the delta H. We've looked at this before. The heat, basically, the energy that is required to break a particular bond in 1 mole of a gaseous substance. Now, that's a mouthful, but easy way to just think about this is how much energy does it take to break apart, to break a bond. Okay. Now we use the letter D and the bond that we're looking at to represent the bond enthalpy. Okay, so if we're looking at this Cl2 molecule right here, and we want to break it into 2 separate Cl atoms, we're trying to look at the strength of this bond right here, right, between the 2 Cls. So if I wanted to talk about that bond, I would write D parentheses and then just draw that bond, okay, to show that that's the bond enthalpy that I'm looking at in that situation. Basically, just how much energy does it take to break that bond? Okay, and then there's going to be some kind of delta H value. All right, now that's for diatomic molecules when there's 2 atoms in the molecule, but we got more complex ones that we've already looked at. Polyatomics. Polyatomic, again, poly means many. So when we have an atom that has multiple bonds, so here we have methane, CH4, and we want to turn it into all the parts that make up methane, right? We want to make it into a carbon. We want to turn it into a hydrogen. The amount of the bond enthalpy for that molecule is going to be the sum when you add up all of the how much energy it takes to break all the bonds. So here we have 4 separate CH bonds, right? You guys see that? And so if I want to figure out how much energy it takes to completely atomize this molecule, you just need to find out how much each of them, the bond enthalpy of each of them, and then just add them up. In this case, there's 4 of them, and they're the same bond. And so what we can do is multiply it by 4. Okay. So you guys don't need to memorize these bond enthalpies, but you do need to know how to use them to break it apart. On the AP test and on our test in this class, I'm going to give you guys a table usually with the bond enthalpies, and I'll give you a molecule, and you just need to figure out how many of each bond there is, add them up, and that's your how much energy it takes to atomize it. All right, so we're gonna go into a practice problem with this, but do you guys have any questions before we do that? That's chilling. Yeah, you're not gonna have to memorize any of these values. I'll be completely straight up with you. I don't know any of these values off the top of my head, and I turned out fine, I think. Okay, so what I want you guys to do is take a look at this compound, ethane. Okay, the bond enthalpy, the total enthalpy of this molecule is 2826 kilojoules per mole. Okay, and the bond enthalpy between a carbon and hydrogen single bond is 413. So I want you guys to find the bond enthalpy between 2 carbons. Okay, try that out. A little algebra that you'll need to know here. I'll give you guys about 2 minutes. If you want, you can check with your table partner, and then we'll go over it together in just a second. Jaden, can you do me a favor? Jaden. Jaden. Can you take this off? Main office, basically once you go towards the main building, it's basically the first thing right that you'll see it's on the right side of the main office. Marla. Marla. It's up there. Ah, shoot. I should have been Starbucks and yelled your name wrong. Marlin?
Maria.
Oh, Maria? It's okay. Somebody wrote my name as Pale before. Legit. P-A-I-L. Y'all doing this on purpose at this point. I can see that. All I want is for them to say ping. I really want them to call me ping.
Why?
I think it's funny. Because that's the typical like Chinese name in the movies. I want to be called ping. Let's see what I think it's Rush Hour. But it's like, oh yeah, that's Rush Hour 3. Dude, I love Rush Hour. Dude, their Chris Rock and Jackie Chan's chemistry is amazing. It's in a yellow box on the cabinet.
Jackie Chan, instead of saying green, like cheese.
I remember. Classic movies. Classic. All right, you guys ready to go? Okay, so in this problem, it's important to identify what we're looking for, and we are looking for the enthalpy, or sorry, the value for the bond enthalpy for this bond right here between the carbon and the carbon. So this line. Okay, we know that the entire molecule, the bond enthalpy is 2826 kilojoules per mole. And so in order to find this guy right here, that means I just need to subtract all of the carbon hydrogen bonds, not bombs. Okay, because if everything is 2826, right, the sum, that means I can find out the carbon-carbon bond enthalpy by subtracting these 6 carbon hydrogen bonds. Okay, so what I'm going to do is pull out my calculator, and then we just need to take the carbon hydrogen bond, which is 413, multiply it by 6. That's 2428. And so all you need to do is subtract that from 2826. Okay, so I can just go back to my calculator, 2826, and then it's just going to be the negative of that. So, oops. It's going to be 348. So that means that the carbon-carbon bond enthalpy is 348 kilojoules per mole. Okay. Yeah.
Is there ever an example where like because atomization is where it all breaks apart, right? Where it just doesn't all break apart.
Yeah. Like where it doesn't all break apart? No, it's usually gonna, this bond enthalpy is talking about atomization, so no. So you mean talking about like breaking one bond?
Yeah.
Yeah, I mean there could be examples like that, but you would use the same steps for that. Good question. Alrighty, let us move on. So again, like I said, there's always going to be a table for these bond enthalpy values, and then you guys can probably guess the bigger the number, the more energy it takes to break that bond. So this table is 8.4 in your book. Again, you guys don't need to memorize any of these. You're always going to be provided the bond enthalpies. But it is nice to kind of know the trends that you guys will be able to see. Now, if you guys notice, what I mean by trends is if you look at the single bonds, the values are typically smaller than when there's multiple bonds, right? So like a carbon is 348. Single bond, but a double bond is 614 and a triple is 839. So it's just nice to know those trends off the top of your head, but you guys are already familiar with this. The more lines there are between those two elements, the stronger the bond. Okay. Any questions? Chilling? All right. Okay, so I think this is kind of what you were getting at, Josh, but now we're going to be talking about enthalpies of reaction. Okay, now in an enthalpy of reaction, what we do is we use the average bond enthalpies to estimate the enthalpy of reaction. So basically, I can give you the structure of the chemicals we're looking at, and then you should be able to determine whether or not it's exothermic, endothermic, or whether about how much energy it takes for that reaction to occur. Okay. And so this is the formula right here. You guys want to write this formula down. The delta H of a reaction, the enthalpy of a reaction, is equal to this symbol. It's a Greek alpha, sigma. We might get to the sigma variant one day, but for sigma just means the sum. So the sum of all the bond enthalpies of the bond that's broken minus the sum of all the bond enthalpies of bonds that are formed. Okay, so I'll show you guys how to use that equation in just a second, but make sure you guys have that jotted down somewhere. The enthalpy of a reaction is basically all the bond enthalpies that were broken minus all the ones that were formed. And that's going to tell you whether or not energy was released or absorbed in that reaction. What up?
I'm looking at 9.22, and will it ever like go from like, oh, you have to go like for water, it's like you have to go from frozen, from ice to water to gas, and then break up to gas?
Oh, that would be a great FRQ question. But no, I've never seen a question like that. But yeah, that would be a great question. Thanks, Josh.
Oh. You should get to look at it though.
Nah. You should get tarred and feathered for that kind of idea. No, I think we should bring back public shaming. I think there were less troublemakers when there was public shaming. Thanks, Jaden. We can just throw that up here. All right, so let's take a look at an example just to see how we use it. So here we have an equation where we have the decomposition of N2H4. You have an N2H4 molecule, and it's breaking down into N2 and two separate H2s. You guys all see that? See what's going on in the reaction? Now, in order to find the delta H of this reaction, what we need to do is we need to figure out what bonds were broken and what bonds were formed. Okay, so this is an easier problem because we only have one molecule that's breaking down. So let's just think about this. What's one of the bonds? What type of bond was broken in this molecule? What's single, but single between what elements? Yeah, so we got a nitrogen-hydrogen bond, right? Okay. You guys see that? There's a nitrogen and hydrogen bond. How many nitrogen-hydrogen bonds are there that were broken? Yeah, no. Oh, 4, my bad. I thought you were throwing gang signs at me. We got 1, 2, 3, and 4. So we had 4 nitrogen-hydrogen bonds that were broken, right? So all right, broken. 4 different relationships that were broken. And then what's another bond that was broken? Yeah, and then we got the NN. So we have 1 nitrogen, nitrogen. Okay. So far, so good? All right, so what we're gonna do is we're gonna go back to that table up there, and I want you guys to figure out what the total amount of energy it took to break this molecule. Okay, you're gonna need to use the table up there, and you should be able to find a nitrogen, hydrogen single, a nitrogen, nitrogen single, and then just add them all up, and that's gonna tell you the total energy it takes to break apart this molecule. Okay, so you're gonna scroll up, and you're going to take a look at this table, okay? Everyone's been working hard, so it's all caught up. Thank you, though. Alrighty, guys. So if we take a look at the nitrogen, what's the bond enthalpy for the nitrogen bond? Yeah, we got 163 right here. And then what about the nitrogen-hydrogen? Yeah, we got 391, which means when we go down here and we take a look at our equation, the nitrogen-hydrogen bond we said is 391. So we're going to have to multiply that by 4 because 4 of those bonds were broken, right? 391 times 4. And then there was one nitrogen-nitrogen bond that was broken, which is 163. Okay, and if we add those up, we can figure out how much energy it took to break apart this molecule, to atomize this molecule. So if we do some math, you should see that if you add them together, you should get a total of 1727 kilojoules per mole. Okay, so the amount of energy it takes to break apart this molecule, to atomize it, is going to be 1727 kilojoules per mole. Okay. Everyone got that answer? Yeah. All right. So I'm going to write that right on top right here, just so we have a little bit more space to work with. Okay, now I want you guys to do the same thing for the other side of the reaction, because these are the bonds that are formed now, right? I want you guys to take about a minute, or I guess 2 minutes, to identify what kinds of bonds were made and how much energy it takes to make them. Okay. So now we're going to go with the other side. I want you guys to figure out how much energy or what bonds were made and how much energy it took to make them. Okay, same thing. You're going to look at the chart again. Alrighty, guys, let's go over this. So what's one of the bonds that were formed inside this reaction? Yeah, we got a nitrogen triple. There's one right here. And then what's another one that was formed? Yeah, a single between a hydrogen. But there were two hydrogen H2 molecules that were formed, right? Which means that we're going to have two of these. You're going to have to multiply this by 2 because we formed two separate H2 bonds. Okay, so we're going to go back up to the table, and I want you guys to tell me what the values are. What is the enthalpy for a nitrogen triple bond? Yeah, we got 941. What about, and then we already did hydrogen, right? Hydrogen, or we didn't do hydrogen. What's hydrogen? Yeah, we got 436, and then we have to multiply that by 2. So the total amount of energy that it takes to form this is going to be 1813 kilojoules per mole. So the energy it takes to form all of this is 1813 kilojoules per mole. Any questions? All right, so we're almost done. Now we need to calculate the entire energy. So first thing you want to do to find the enthalpy of the reaction is you want to take the sum of the bonds that were broken. This is what it takes to break everything. So 1727, and subtract it by the bond enthalpy of the bonds formed. So minus 1813, and that's going to give you negative 86 kilojoules per mole. Okay, and so if it's negative 86 kilojoules per mole, was this an endothermic or exothermic reaction? Yeah, exothermic. It's releasing energy. Oh, wait. Am I tripping? No, it's correct. It's exo. Yeah, sorry. It's too early, guys. Alrighty, you guys ready to move on? Okay, we'll do a couple more and then we'll take a quick break. So same thing with energy. The more energy there is in a bond, the shorter the bond length. So same thing that we learned before. Single bonds have the least amount of energy, so they're the longest. And then double bonds have a little bit more, so they're shorter. And triple bonds are the shortest. You can see these by the angstrom. Angstrom's like a measurement for distance. Single bond is 1.54, gets shorter with the double and the shortest with the triple. Same thing with the energy. The shorter the bond gets, the more energy there is. Okay. All right. And I think this 9.23 is not the last question. Never mind. Okay, so we're going to put everything together, and this would be kind of like a bomb FRQ question, because we're taking a bunch of different concepts that we learned, and we're going to be putting it into one big problem. Okay. So 9.23, what I'm going to do is first read the question to you guys kind of slowly. So try to absorb what's going on. That's the first thing you usually want to do in an FRQ. Just figure out what the information is. If you want to jot down some of the stuff on the side, you can. Okay, phosgene, which is actually one of my favorite chemicals. It's a substance used in poisonous gas warfare during World War I. Okay, and it's named so because it was first prepared by the action of sunlight on a mixture of carbon monoxide and chlorine gases. So if you guys ever get your hands on carbon monoxide and chlorine gas, and you put it in the sun, you can make phosgene. Okay, its name comes from the Greek words phos, light, and genus, born of. Okay, phosgene has the following elemental composition. It's 12.14% carbon, 16.17% oxygen, and 71.69% chlorine by mass. Okay, and its molar mass is 98.9 grams per mole. Okay, so the first thing you want to do is determine the molecular formula for this compound. Okay, so I'm going to give you guys 2 minutes to try this out. We haven't done this in a while. If you guys don't remember, this is empirical formula to molecular formula. And if you don't remember what that is, you might want to go back into your notes. But I'll give you guys 2 minutes to try it out because, again, we do have our midterm coming up where we're doing a cumulative exam. And I want you guys to kind of try to rack your brain, try to get your memory back for these things. So try part A, find the molecular formula. You guys can work together. After that, we'll go over that and then move on to the next parts of the problem. Okay. We haven't done empiricals in like 2 months. Anyone want this? Zebra popcorn? Caramel corn?
Oh, I know that is.
Are you the only one? Anyone else want it? Okay, we're gonna have a competition for this, okay? Really? No, dude. Go for it. Oh, we got Ghirardelli too. I can we'll do a competition for this. And we got hot cocoa. I'll let you make
I
hot
have
cocoa.
those at home.
The worst, man. Huh? You want the cup? Sure, I can give you. I'll give you the cup with the hot cocoa, but you gotta earn it. This is what's for auction right now. Okay, you guys can win these fabulous prizes.
Oh, the cup. Oh, yeah. Like, use it for my point and so much.
This all. Actually, just auction off my candy here. I get so much candy for presents. I can't eat it. Huh? Oh, I mean, I can, and I love candy, but my wife likes my 6-pack, so gotta look good for the wifey, you know.
But she really cares about you.
She does, but it's always a perk, you know. And everyone told me before I got married, "Happy wife, happy life," and I agree. So I have to keep my wife happy.
Kind of coach used to tell us. He was a really young guy too. When we work out or did fitness training, basically just running pain, muscle pain. He's like, we were getting fit for ourselves for the game, getting fit for our girlfriend.
Yeah, that's a good way to think about it. But I'm gonna be honest with you. The most painful realization I had in my life is that girls don't care how much you lift, how high you jump, or what you look, or even what you like, how buff you are. But the boys do.
Yeah.
And so do it for the boys. For the boys. Dude, legit. The only people that compliment my calves or my jumping or my lifting are guys.
I've never spoken to the truth.
It is. It's the most painful realization. All right. Do you guys need a little bit more time for this problem, part A?
Oh, just for A.
Part A, yeah.
Oh, we're just-
I mean, if you guys, yeah, I'll go over part A. If you guys are still working on it, it's all good. If you want to move on to the other parts of the problem, you can. But I'm going to start going over part A, the molecular formula. Okay, so whenever you have a molecular or empirical formula question, basically anything where it tells you the percentage of that, or like what percentage of that molecule is made up of certain elements like this, you always want to start by assuming a 100-gram sample. Okay, because if you assume that it's 100 grams, you can basically just turn this into 12.14 grams of carbon inside of that molecule. There are 16.17 grams of oxygen inside that molecule and 71.69 grams of chlorine in this molecule. So this molecule, you just turn it into 100 grams total, and then you have your percentages right here, okay? Next, what you're going to do is you're going to convert all of these into moles. So I'm going to take the grams of carbon and divide it by the molar mass, right? 12 grams per 1 mole. And that's going to give you your moles of carbon. Same thing with the oxygen. You can divide it by the molar mass, which is 16 grams of oxygen per 1 mole. And that's going to give you the moles of oxygen. And then same thing with the chlorine, 35.45 grams of chlorine per 1 mole. And that's going to give you the moles of chlorine inside of that molecule. So basically, the steps that we just took are, we say that it's a 100-gram sample. That way we could turn the percentages into grams. And then you're just turning it into moles. So what you're doing is you're calculating how many moles of every element are inside of that molecule. Okay? And then I'm going to do the math kind of quickly. I have it written down here. You got 1.011 moles of carbon. You have 1.011 moles of oxygen. And then you have 2.022 moles of chlorine. All right, any questions? Okay, so what we're gonna do now is we're gonna turn this into a form. We're gonna put it into a molecular formula. So we can just assume carbon is 1.011. Oxygen is going to be 1.011, and then there's 2.022 moles of chlorine in there. Now, we can't have a decimal for our subscripts, so we just need to divide by the smallest number, which is 1.011. So if you divide carbon, the 1.011 by 1.011, you're just going to get, 1. So carbon is 1, oxygen is 1, and then chlorine, Cl, is 2.022. If you divide 2.022 by 1.011, what are we going to get? 2. So this is going to be your empirical formula. All right, so I'll stop right there for just a second because we went through a lot of steps. Any questions on how we got the empirical formula? All right, so what we want to do now is we want to make sure that we can find the molecular formula. So what we want to do is we want to find the molar mass of this compound right here, and then just scale it up to see if we can just get it to, what was the molar mass? 98.9. So molar mass of carbon is 12, oxygen is 16, chlorine is 35.45. So if we have 2 of them, that's going to be 70.9. Okay, so if we add this up, we're going to get 98.9 grams per mole. So that means the empirical formula is the same as the molecular formula. Okay, so this is going to be the formula of phosgene, this toxic compound. Okay. Yeah, what's up, Great? Yeah, it's the molecular and empirical because if we find the molar mass of the empirical, it's the thing that we were looking for. But if it was like double it, then you would have to double the empirical formula to C2O2Cl4. But since it's what we're looking for, right? 98.9, 98.9. This is both the empirical and the molecular formula. Okay. Alrighty, so that was a lot of work for one part of the question. It looks like some of you guys are starting the other parts already, so you guys can get started. Now, what I want you guys to do now is take a second to draw 3 Lewis structures for the molecule that satisfies the octet. Okay, and it tells you that the chlorine and oxygen bonds to the carbon because carbon's always in the middle. Now, I only need you to do one of them, okay? I'll show you all three up here, but I need you to just draw one of the Lewis structures that satisfies the octet, okay? Take a second or take a minute or two to do that. Whatever. Yeah, go ahead. Yeah, take those goggles over there so you don't get in trouble. No, on the side of next to the trash can. Do you see that? Yeah, that's my hall pass. All right, I'll give you guys another minute to finish that up, and then we'll go over it. Close one's bungalows, I think. Yeah. We're gonna take a break after part B, so you can go try out the further ones if you want to. Alrighty, guys, I'm gonna start going over the structures. So if you guys want, you guys can follow along or finish up. Okay, so we have COCl2, and we know carbon is in the middle. So we're gonna put carbon in the middle, and then chlorine and oxygens are gonna be around the carbon. Okay, we're gonna start. Well, actually, we should have counted the valence electrons. Sorry. So we have 4 from the carbon, 6 from the oxygen, and then 14 because there's 2 chlorines. So that means we're gonna have a total of 24. Okay. We're gonna start by connecting all of them. So Cl, Cl, O. Okay, and then so we've used 6 of them, so we should have 18 left. And so what we're gonna do is we're gonna start with the most electronegative one, and we are going to put valence electrons on there. So oxygen, we're gonna put 6 on there. That's gonna get us down to 12. And then we're gonna put 6 more on each of the chlorines, and that'll get us down to 0. Okay. So far, so good on why we did it like that. Now, what we wanna do is we wanna make sure that carbon has an octet, and the only way for carbon to have an octet is for there to be a double bond. And so those are that's where we get 3 different structures for this molecule. We can either have a double bond between the carbon and the oxygen. You can also have one where you have a double bond between the top chlorine or one of the chlorines and oxygen. Again, you don't have to orient it exactly the way that I did. Like if you have oxygen on the top and the Cl's on the bottom, that's fine, as long as the connections are the same. Or you can have one where carbon has a double bond to the other chlorine. Okay, so these are the three structures. These are your resonance structures for this molecule right here. Okay. All righty. Any questions on that one? All right, so we'll take a quick break. We'll take a 7-minute break. If you guys want, you guys can go to the restroom. If you guys want to copy all three of these down, because we will need to eventually, you guys can do that, but we'll take a quick break and then come back together. All right, so let's go on to part C of this problem. We're gonna figure out which one is the dominant one using the formal charges, okay? All right, so we're gonna take a look at this this one on the left first, and we're just gonna calculate the formal charge. So let's do that together, and then I'll have you guys try part D on your own. So part C, if we want to find the formal charge of the chlorine right here, we're just gonna do the valence electrons, which is 7, minus the lines, which is 1, minus the dots, which is 6, and that's gonna give us 0. So this chlorine has a formal charge of 0. Now, this other chlorine, it's basically the same thing, right? The same number of lines, same number of dots. So that means this chlorine is also going to be 0. Okay. We can do carbon. Carbon is 4 valence electrons. There are 4 bonds. So 4 minus 4, there are 0 lone pairs. So that means this one is also going to be 0. And then lastly, oxygen is 6. And then there's a double bond, so 2. And then 4, and that's going to get oxygen to 0 as well. So we actually don't need to go on to do the other ones because we have a structure that's where everything is 0, where everybody is happy, right? And so this tells us that this structure right here, where the carbon has a double bond to the oxygen, is the most stable. Any questions on that one? So that means that the other ones right here are poo-poo stinky. We don't care about those. Alrighty, so last but not least, we're gonna finish off with the bond enthalpy stuff. Now, what we're gonna do is we're gonna have to estimate the formation of gaseous phosgene, which is this compound right here. And we need to do that based on the reaction between carbon monoxide, CO, and Cl2. So let me actually redraw this. Sorry, guys, So we have CO plus Cl2, and it's forming phosgene. So it's going to be COCl2. We just drew phosgene as a O double bonded to a C, and then there's 2 Cl's. And so what you need to do is you need to figure out basically how much energy it takes for this reaction to occur or how much it absorbs. Now, in order to do that, you need to know what CO and Cl2 look like, right? And so in this problem, you have to do a bunch of things. First thing you want to do is find out what the structure of those 2 other compounds are. You want to figure out what the Lewis structure for CO and Cl2 are. After that, you're going to figure out what bonds are broken and what bonds are formed. We're going to refer back to the table and then calculate what the enthalpy of the reaction is. Okay, so a lot of stuff going on here, kind of similar to what you'll see on FRQ, but I'll give you guys about 2 minutes to try it out. See if you guys can start off by drawing the structures for COCl2. Then we'll start going over it, and if you aren't done yet, we'll finish it up together. Okay, so take about 2 minutes. Try to find the structures of CO and Cl2. Thank you. Thanks. It's delayed, but I'll take it. Dude, people nowadays have gotten so rude, man. When I used to sneeze, everyone used to say, bless you, like you guys. But now everyone just looks at me like, you know what I mean? Can't even, remember the beginning of COVID? You couldn't even cough in public. People would just stare at you.
Oh my god.
Freaking rude people, man.
When COVID first started, but like before I was like, oh, stay at home.
Yeah.
I sneezed, because I ended up like, you know, when you like swallow air around.
Yeah, no, it happens. People just sneeze and cough. It's a normal human like activity.
Exactly. I swear to God, I was like around like they were like right next to me, but they're like 5 feet apart. I was like, right? And then they full on went. One even across the street. I was like, damn.
Rude people, man. Dude, you don't know how many fights I got into people about like COVID and stuff. Like I would be at the park, like just working out it, like middle of a field by myself. This one person, this one lady, like yells at me, starts coming towards me, like, wear a mask. And I'm like, I'm outside, lady. And she's like approaching me. So I'm like, dude, 6 feet, man. Stay away from me, lady. If you're that scared of COVID, stay inside. I don't know. I think the problem with COVID is that people got too used to telling people what to do now. It is. It's virtue signaling. It's like, look at me, look at me, look at me. Look at how good of a person I am. Anyway, that's Mr. Social Commentary for today.
Social commentary. There you go. That's the name we're looking for.
Social commentary, dude. I just want to be left alone, man. Just don't tell me how to live my life. I don't tell you how to live yours.
That's my right.
Yeah. Like if I had it my way, everybody would give me free money and free food. Alrighty, guys. I'm gonna get started with drawing the structures. If you guys are still working on it, feel free to kind of zone me out for a little bit and finish up. But I'm gonna get started just for the sake of time. I think this is the last problem we'll solve. Okay, so we have CO, and for CO, you should have this as your structure: carbon triple bonded to an oxygen. And then for Cl2, you should have Cl single bonded to another Cl. Everyone got that? Hopefully. Now, we want to start off by figuring out what the energy of breaking the bonds are. So super simple for the breaking. You're breaking one carbon oxygen triple bond, right? Not too much to say there. And the carbon oxygen triple bond is going to be 1072 on the table. The other bond that you're breaking is going to be a chlorine-chlorine single bond. And if you look that up on the table, you should get 242. So that means the total value for the bond enthalpy of the bonds that you're breaking is 1072 plus 242, which should give you an answer of 1314 kilojoules per mole. Okay. All right, now in terms of the bonds that were formed, we can see that the first bond, one of the bonds that we form is carbon double bonded to an oxygen. And then we have a carbon single bonded to a chlorine, but we have two of those. So we have to multiply that by 2. Okay, so carbon oxygen double bond is going to be 799. And then we're going to add that to the carbon chlorine, which is 328, but we have to multiply that by 2. And so the total value for the bonds that were formed is going to be 1455 kilojoules per mole. All right. So there you go. I know that was a lot of work, and especially if you think about the other parts that we did, that's a lot of work for one problem. But this is the kind of stuff that they might throw at you during the FRQs. And you have 7 FRQs during the test and 105 minutes to do it. Usually there's 2 long ones like this and then 5 shorter ones, but just make sure that you're aware that you're going to be doing at least 2 problems like this, where it's like multiple parts that kind of carry on to one another. All right, well, let's finish this up. If you want to find the delta H of the reaction, what you want to do is you want to do broken, the energy broken, or the energy in the bonds that are broken and the minus the energy of the bonds that are formed. So you have 1314 minus 1455, and that'll give you a final answer of 141 kilojoules per mole for this reaction. Oops. All right, and with that, we are all done. You can't even see that, huh? Sorry, 141. All righty, guys. Well, that's going to be pretty much it for today. Next time that we meet, I guess next month, Tuesday, we are going to be finishing up Unit 9. And then on Thursday, we're going to do a FRQ practice day where I'm going to go over some tips on how to do the FRQs well. And then after that, we have our final. And then we're done. All righty, guys. Have a good one.